This is a very exciting occasion. Geoffrey has been working with me for 4 years, and it's been a very exciting 4 years. You know, many students take some time to sort of get into the mojo of research, but Geoffrey more than hit the road running. In fact, I always encourage my students, you know, to send me before we meet each week some little thing, you know, an idea, an example, a hypothesis, a provocation. And Geoffrey, from the very beginning, started sending me these extraordinary videos, video demos, often faked, of ideas of things he wanted to build. And in order to impress upon you how remarkably effective Geoffrey's been as a student, I thought I would dig into my email and find the first date that Geoffrey sent me such a video to see how close it was to the beginning of his graduate career here. Well, it was actually 5 months before he even started. A couple of weeks after he was accepted into the program, he started sending me his first videos. So it's been a real blast. I want to say that, you know, actually, in some respects, a lot has changed since Geoffrey started. And in case you think that Geoffrey's infallible from the quality of his research, I do want to read one quote from an email he sent me when he started. And here's what he said. We're talking about building end user software and the role of AI in doing that. And he says, I've thought about whether a similar approach could be applied for making programming accessible to end users, but it looks like a dead end to me. Machine learning approaches are a good fit for problems that operate in continuous high-dimensional spaces, such as images, but programs don't fit that profile. So I thought that was pretty funny. Of course, Geoffrey was not alone. And in fact, I think he probably has been ahead of the curve in recognizing the potential for AI. Despite so much changing, it's also intriguing to me that so little has changed. And when I went back and reread some of the emails that Geoffrey and I exchanged shortly after he was accepted into the program, it was amazing to see how many of the ideas that he's going to tell you about in his presentation today were already germinating in his head then. And I just want to close by saying that aside from, you know, the incredibly rich intellectual experience of working with Geoffrey over the last few years, it's been wonderful to learn so much from him about so many things. Some of you might not know, Geoffrey is an absolutely amazing at sort of organizing meetings and figuring out how to get participation and all these sort of creative ways to review things. And I've learned a lot from that. Evidently, things I hadn't learned in about 30 years of research that Geoffrey's taught me. And so I want to say it's been just the most wonderful experience working with Geoffrey, and I'll certainly miss him. But with that, I'm very excited to have Geoffrey present his work to you.
Awesome. Thanks so much for that kind introduction, Daniel. It's really good to have all of you here in person and on Zoom. Thanks all for being here. So I wanted to start today with a little story. It's a story about an experience that totally changed the way that I think about the creation of software. And it's sort of one of the reasons that I'm standing here today presenting this work. Before coming to grad school, I worked at an education technology company called Panorama. And what we essentially did was we helped schools run surveys of their students. And then we would make these data reports in this web application where they could log in and see all the reports and all these beautiful data visualizations. And we worked really hard to make these reports nice for them. And for the most part, our users loved these reports. But I'll always remember there was this one user feedback call that we did that stuck in my mind. And we got on this call and we were talking to this principal and asking them, what do you think about the latest reports? Do you like them? Do you dislike them? And there's sort of this awkward silence. And the principal said, oh yeah, I've actually never seen your data reports. We don't use them. Okay, what do you mean? And they said, actually, the best feature you guys have ever built is export to Excel spreadsheet, because then I can get the data and make my own report, which is way better than yours. Oof. Sort of a tough blow. But then, okay, intriguing, right? We asked, can you show us? And they show us something that looks like this. This is a very, very rough reproduction. It was very ugly. It was very simple and basic analyses, nothing close to what we had done. It was essentially untested, so very error prone. In many ways, it was worse than what we built. But in other ways, it had these really intriguing advantages. They were able to group students exactly the way they thought about grouping in their schools, just by pulling in other spreadsheets they already had lying around. They could do the design themselves and pick colors or layout or even vocabulary. And these are things that might seem trivial, but actually things like vocabulary can really matter when you're communicating these sensitive results to people. And so what I realized is this sort of reflects two fundamentally different ways of thinking about the creation process for software. On the one hand, you have this very centralized process where you have this room of professional engineers and designers in Boston trying to design one app that can be used in thousands of schools across the United States. And on the other, you have this much more decentralized approach where people in those schools are designing software for their own unique needs. And there's a lot of those unique needs that they can address because they have that local knowledge that you simply can't address, from an office in Boston. And so that got me thinking, hold on, why are these two worlds so separate from each other right now? There are these sort of ceilings on how far you can get with a spreadsheet. And then on the other end, the tools that we use as professionals to build these sophisticated web applications are tremendously complicated, way more than a principal in a school can handle. And so that raises this question, why can't making apps just be as easy as using a spreadsheet? I got really interested in that question, so interested that I ended up doing a whole PhD in that topic. And today I'm excited to share a few of the things that I've learned investigating this question. I'm mainly going to show you today 3 systems that each illuminate sort of different aspects of this question. The first tool I'm going to show you is called Wildcard. It's a tool where you can take existing web applications that you're already using and then make small customizations to them through a spreadsheet-like table UI. The second tool, called Potluck, is going to show how you can take text notes, like a note you would write into Apple Notes, and bring computational tools into that text note using spreadsheets. And then the final tool I'll show you is called Riffle. And Riffle is a tool that enables you to build more complex, high-end applications. It's targeted more at technically sophisticated users, but it brings some of these beautiful ideas from spreadsheets and databases into that process to make it simpler to build these high-end applications. So that's the basic roadmap for today. First, though, I want to take a step back. All this stuff I'm going to show you today is building on some foundations of really neat ideas that have come before. So I want to just briefly introduce you to a few of those ideas. So here's the first question. What is it exactly about spreadsheets that makes them so great? Maybe you love spreadsheets, maybe you hate them, you probably use them. They're a very successful example of what we call an end-user programming environment, a place where non-professional engineers and programmers can just build software for themselves. Personally, I think there's a few factors that are worth pointing out here. Some of them are a little more obvious, some are more subtle. First of all, this 2D grid, you can just put data anywhere on it in any shape. You don't need to come up with a data schema in advance. It's very flexible. Of course, spreadsheets are famous for reactive updates. When you update a cell, everything in the spreadsheet automatically updates, so you don't have to manually think about that stuff. Spreadsheets primarily show you data and not code. So most coding environments that professionals use just show you walls of textual code. But in a spreadsheet, you're mainly looking at the data you're working with, and the code is just in these little formulas behind the scenes. That gives you a more concrete sense of the data you're working with. Spreadsheets also have lots of really helpful built-in functions that are sort of tilted towards the typical things people want to do in spreadsheets, so you don't have to reinvent everything from scratch. Now, there's 2 more that I think are a little less often mentioned, but are really interesting. One point is that user input in a spreadsheet is just regular data. So let me give you an example of what I mean. This is a spreadsheet for doing a user growth projection. And the way you use a simulation like this is there are these little assumption cells here. And you just change those assumptions and see what happens in the spreadsheet, right? Now, the interesting thing is those are just spreadsheet cells. So what does that mean? I can save this spreadsheet and send it to you. And now you have those assumptions. I can make 5 copies with different assumptions. I know that the reactive updates are going to work as I edit these cells because they're just cells in the spreadsheet. Okay, this all sounds sort of like familiar stuff. Maybe it doesn't seem that cool. But actually, if you think about it, a lot of other more fancy application programming environments don't have these properties. If I enter stuff into a form, it's not automatically saved. It's hard for me to share it with you. I might need to resort to screenshots. There's a real uniformity to the way that all of these different kinds of data are handled on spreadsheet. And we're going to see this theme come back later. The final thing that's really neat about spreadsheets is that the modularity of a spreadsheet enables really interesting forms of collaboration, especially between more beginner and advanced users. So a very common workflow that happens in spreadsheets is that a more novice user might fill in most of the spreadsheet, and then maybe they hit the limits of their knowledge. So they can go ask for help, and someone else can help fill in the details of a complicated formula. But because of the way that spreadsheets are structured, it's often easy to just fill in a little bit of a formula and then hand the spreadsheet back to the beginner and have them keep going with the rest. It sort of separates out the tasks in a nice way. So these are a number of benefits of spreadsheets that you'll see sort of threaded throughout this talk. But there's been sort of another parallel track of work that's also existed for decades alongside spreadsheets that I'm drawing from as well, which is low-code database toolkits. So you may have encountered products like Microsoft Access or FileMaker Pro, and these are applications that have much more structure to the data than a spreadsheet. So they typically have a relational schema, and they let you build all sorts of different interactive views over that database schema. Things like forms for data entry or reports for aggregation. And they let you build simple apps that are CRUD apps, create, read, update, delete. Essentially, these are just simple wrappers around a database where you're editing and inserting and deleting records. Now, both of these lines of work have existed for decades. And in the past 10 years or so, there's been a bunch of interesting work in both commercial and research spaces that has combined some of the best aspects of both of these categories. Here's a pretty famous now commercial product called Airtable, which is a good representative of this more recent class. I'll show you some things you can do in an Airtable. You have this table of data here. It has more structure to it than a spreadsheet. So for example, I can click on a column and see that there are these specific values which I'm allowed to enter it. It also directly models associations across these tables. So there's this column here, which is linking to another table. Here's that other table. And Airtable understands this link in a rich way. So I can click through and see that link to that other table. This is something that spreadsheets typically don't have as good support for. I can also construct in this UI all sorts of different views of this data. So I can say I want to group this data by this column, and it'll create a grouped view, right? But I'm not limited to that one view. A big part of this sort of tool is that I can see multiple views of the same underlying data. So I could see a different grouping by a different field, or I could even see, give me one column per status and show me cards. Or maybe I even want to see a calendar where I pull in one of these date fields on these records and show them on a calendar. And these are all sort of very generic views that are useful for all sorts of different tasks. They're useful ways of seeing the same data in different ways. Airtable also borrows spreadsheet style formulas. So for example, here I have this column for an expected close date. And I just want to have this field of how many days is it until it closes. And I've implemented that with a formula here that calculates how many days is it from today to the expected close date. And you can see it computes those numbers here. Now it's reactive, so if I update the date, the formula automatically updates. So this is sort of like a spreadsheet, right? It's a little different because that formula applies to our structured data and it goes down the whole column, but it's sort of a similar idea. So there's a bunch of commercial products which now use similar ideas, products like Coda, Notion, Glide. But there's also been some really interesting research projects, many of them here at MIT, which have studied different combinations of these ideas to sort of probe different parts of this design space. Here's one project that I have found very, very influential. It's called Quilt by Ted Benson, Amy Zhang, and David Karger. And they had this really elegant idea, which is, what if we literally make an app with a spreadsheet? So we'll just have a spreadsheet which has some data and some computations. We'll let you specify a view in HTML that binds to that spreadsheet. And then what you get is a little UI like this that has a visual design, but it's backed by a spreadsheet. And there's been other projects that sort of take similar approaches of weaving together spreadsheets with interactive views. I don't have time to talk in too much detail about these right now, but happy to talk more about them later. Now, there's been other projects which take things a little bit more in that structured database direction. Here's one example of that sort of work. It's called Object Spreadsheets. This is work by Matt McCutcheon, Jahari Zaki, and Daniel Jackson. And here they said, OK, we do want to build apps with spreadsheets, but we want to apply a little more structure to the data format. So they work with tabular data. They even support things like nested tables. And applying that structure solves some of the problems you have from using naive, unstructured spreadsheets. And again, there's been a lot of various work that is a little bit more on the structured end, exploring different ways of building interactive user interfaces over structured databases. All right, so now we've laid sort of a brief foundation about this space. Now I'll get into sharing with you some of the systems that I've built during my PhD. Okay, so this first system here is called Wildcard. It was built together with Daniel as well as some UROps, Tyler Millis, Jessica Quay, Kapai Katonga, Catherine Jin. And the idea we were thinking about was, it's not always the right thing to build an app from scratch. In fact, most of the time, you already have a piece of software you're using for something, and it might be nice to just be able to make a little tweak to that existing app, right? The problem is, in typical traditional computing, making that little tweak can take tremendous amounts of work and basically requires programming skills. So we were wondering, can we bring down that barrier a bit? Here's the model we came up with. It's called data-driven customization. It's a super simple idea. You start with a UI, and you pull up a spreadsheet-like table from the bottom, and this spreadsheet kind of shows you the underlying data that's in this UI. And then all you need to do is start making edits in that spreadsheet. And what we do is we keep the original UI and that spreadsheet synced with each other. So when you edit the spreadsheet, you also are editing the original app that you were using. Let me show you some examples. This is the grocery website Instacart. I was using it a lot during the pandemic. And one thing that bugged me about Instacart was they have this order form at the end where they show you what you bought, but you can't sort it by price. And I wanted to sort it so I could see what were the most expensive things we were getting and do we really need them? So here's how I do that in Wildcard. I open up a table and you see the groceries in there. And what I'm going to do is I can click that price header. And when I click it, it's going to sort the table, but also sort the original web page. Okay, great. Now the website's sorted. I can view the items in the order that I wanted to. And at this point, I can just close up that table. I've done what I need, and I can go along my way, keep using Instacart, right? That's a very simple direct manipulation interaction that I was able to use to do that customization. Okay, another thing that bugged me about this website was that I couldn't take notes on these groceries. And sometimes I just wanted, it's like making little scribbles on your grocery list, right? Notes to yourself. This is very natural in a spreadsheet. I can just go to this column to the right and enter a note. Do we really need 3 cereals? Is that, at the time I was eating a lot of cereal, so the answer was yes. So I fill in these notes, and you see they appear also in the original website, not just in that table. They're also actually saved on my computer. So anytime I come back to this grocery order, I'll hit reload there to show you, those same notes come back and appear on the table. And the thing is, I didn't need to bug the Instacart team to build an annotations feature or anything. I was just able to do that myself. Now, where things start getting really interesting is when we bring in spreadsheet formulas to the mix, because that enables richer computations. So to show you that, I'm going to show you this other use case. This is a popular news website, Hacker News. And at some point, I realized I really like the longer articles people link to, which go more in depth. So I want to see how long each article is, and then see the longest ones at the top. Let's do that in Wildcard. Open up my table, same thing as before. I can sort by points or whatever. But this time, what I'm going to do is actually go over here and write a formula. We have this built-in function called read time in seconds, which you give it a URL, and it will try to figure out an estimate for the read time. Now, seconds is kind of a weird unit, so let's get it into minutes. We can just divide by 60. Okay, those are ugly numbers. Let's round them. Great. And then at this point, I can just say, I want to see this column of data in the web page. There we go. It shows up next to each article. It'd be nice to have a label on it so we can do a little more spreadsheet formula programming, add a label. And okay, great. Finally, we can sort too. So let's sort by that number. And just like that, we have the longest reads at the top, and we see a label for each one. And again, I've sort of implemented this customization in the table. Now I can just close it up and go along using the website. Every time I come back, that same code is going to run again. But it felt just like using a spreadsheet, right? That's the basics of Wildcard. I'll show you one last final thing, which is that I can also use this table as kind of a routing point for custom UIs to intervene and replace the UIs of the existing website. So here I have a flight search form for booking flights. And something I find really annoying about flight searches is that I have the dates I want to travel in my calendar, and I need to make sure that I copy paste them exactly right into my flight search, or else things will go badly at the airport, right? But I sort of have limited tools on my computer to do that easily. And Wildcard actually enables a really neat workflow that makes that easier. So here, I've pulled this form into a 1-row table where each cell is one of the inputs. And when I edit the date, I don't just have the raw table view. I actually have this date picker that pops up. And this date picker has my calendar in it. When I click on a date, it enters the data into that cell, and then the table routes it into the form. So now the data has been entered into that form as well. So you can see Wildcard kind of lets me bring in my own custom UIs to an existing website. And to summarize, we've done similar customizations across a broad range of websites. And we found that just by composing these simple primitives, you can do a surprisingly large number of useful things across a ton of different websites. Okay, now you've seen sort of what Wildcard does. I want to show you a tiny view of sort of under the hood, how it works and how to think about it. And to preview, I'm going to use this same schematic diagram across the 3 projects I show today. So there'll be some sort of shared themes that I'm going to demonstrate. So what's going on in Wildcard really? Well, we start with this original web UI. And then what I do is I establish a connection to a tabular data set, right? And the way that works in Wildcard is that a developer writes some code that scrapes data out of that UI and then synchronizes changes in the table back to the UI. Now, once a developer has written that bit of code for a website, end users can come along and use the table in the way that I showed you. Now, the main view I showed you is the spreadsheet table view of the tabular data set. We can do things like sort and filter the table. We can write formulas. As I showed you, those affect the original UI, right? I also showed you that you can bring in your own private annotations and add them to that tabular data set. And finally, we saw with the date picker how you can bring in custom UIs that are different from this table view and also coordinate the data for those through the tabular data set. Okay, that's it for Wildcard. I'm going to take quick clarifying questions during the talk, but do you mind holding longer questions until the end? If it's quick, we can do it now. Yeah, the short answer is that, repeat the question. So the question was, how do you interface with the UI of the site? The answer is that this site-specific adapter, which a developer needs to write for a website, contains all the logic needed to do both scraping and interacting with the DOM of the website to put changes back in. So they just write normal code that does those things. Yeah. All right, let's move on. Now, the second system I want to talk about starts from a slightly different point. One of the really interesting things about spreadsheets is that when you start out using a spreadsheet, you don't necessarily need to have an app in mind. You can just start writing down some data, right? In fact, many spreadsheets have no formulas at all, just tables of data. And in Potluck, we took inspiration from this idea and applied it to a different kind of data, which is text notes. So text notes are probably one of the simplest and most flexible ways you can write down information on your computer or on a phone. There's really no ceremony to it at all. Here I have a coffee recipe that I was really into last summer. Super simple, right? This is basically, simulating a typewriter. Now, the problem is, even when you have this note on a computer, if it's in a notes app, you typically can't bring any computational behavior into that note. And sometimes there are these little computational behaviors that would be really useful to have. Like, what if I could double the quantities in this recipe immediately, or maybe set a timer for this 2 minutes I need to wait, right? So what Potluck is it's a computational note-taking tool where you can start from text notes, but then bring in behaviors like that. So here I can scale up my recipe, like I just said, or whatever time I set for the brew timing. Oh yeah, I can also edit this text, and you can see it sort of live updating that scaled quantity. And then if I just type in a brew time, I'll get an interactive timer. I can just click and start counting down right in my text note. And all of this behavior was specified and built within Potluck itself. The way we do this is a workflow we call gradual enrichment. It's really quite simple. You start out with just a text note. Then a user writes what we call searches, which are patterns that extract structured data into a spreadsheet-like table view where you can specify computations. And then we bring the results of those computations back into the original text note as annotations. And just with that workflow, we can build lots of useful tools. So now let me show you actually how I built that demo I just showed you using this workflow. Here's my coffee recipe that I started out with. And I can click on this search panel over here. And what I'm going to start by doing is entering just a string of text that I'm looking for. It's just like using AppleF. So to find the quantities, let's see, I guess 11 grams is a quantity. So I could type 11 grams, hit enter, and I'll get a search result. Now this is a live running search. So anytime I type 11G into this text document, it will notice that and add another search result. Okay, great. So The thing is, I want to find all the quantities, not just 11 grams though, right? So I can generalize this a little bit and use a named pattern that's built into the system called number. So I can find all the numbers followed by G. That catches the 200. I can also use a little bit of additional syntax to pull out just the number part into its own column. Okay, great. Now I have numbers for all the quantities that have appeared in my text doc. Okay, let's say I want to, and I can delete that extra one there. Okay, let's say I want to double all these quantities now. We'll use a familiar interaction that we saw in Airtable. Open up a new column, type in a formula. Let's say amount times 2. There we go. We have doubled quantities. I can name that column. And then finally, I get to decide how do I want those quantities to show up as annotations. I can show them next to the original text in the document. I can show them above, between the lines. In this case, let's go with a replacement. Okay, and now I have this live thing running where anytime I type a number followed by G into this document, it's going to double it and replace it. Very close. The one last kind of little thing is it'd be nice to have a label to get back that G, right? And that's where I'm going to reveal these formulas that we're typing. Although we have helpers that make them feel like spreadsheet formulas in simple cases, you can also just type arbitrary JavaScript expressions into these boxes. So in this case, because I know the JavaScript string interpolation syntax, what I can do is just edit. I'm just going to edit this formula and add a label to the end. And there we go. Now we have our ingredient doubling. So now I'll show you a few other things that you can build with these same simple tools. Here's an agenda doc for a meeting. You've probably been in a meeting that was running late before. One thing that can really help you keep on track is the times for when things are supposed to begin and end, right? This is a doc where you type a start time, and then you type how long is each thing supposed to take. And on the fly, it's just going to tell you when the segment starts and ends. If things change on the fly, you can just edit this document. You don't need a whole app to do this. Here's a cash register for a bake sale. Set an emoji and a price for each item. Then just type in emojis and see tallies for the prices, right? Here is a plant watering tracker. So I write down all the plants in my house, how often I need to water them, when they were last watered. We also have these little buttons that you can click to say, I watered this today. And basically, it turns red if it's time to water the plant. It's green if you're good. And the general point is that these sorts of utilities, you can go to the App Store and find apps for them. But in fact, they can often be achieved with these very simple tools just within a lightweight text note. Another interesting thing is that you can combine all sorts of different tools in a single document and pull them in. So here's a doc we have like to-do lists getting crossed out. When I mention people's names, they get formatted. We have timers running. And we get to pick and choose all these different tools we want in our context. We don't need to pick a single app. Okay, so now you've seen a bit of what Potluck can do. How does it work in this diagram? Well, in some ways, it's similar to Wildcard. We started in this case with a text note. And what we did is we extracted out data, right? You saw those searches, and we got it into these tabular data sets. And once again, we stuck some spreadsheet-like table views on top of those tabular data sets. That immediately gives you visibility into the search results, but it also acts as a way for you to be able to write new formulas. And then we showed how those formulas get overlaid back in the text as annotations. Now, one thing I haven't shown you yet is that in Potluck, we can also do the same trick of using this tabular data set to support other views besides just the table view. So here's a calendar view of an extracted data set for my gym log workout note. And what I'm going to do is I can type a new workout into my note here. I like doing this because it's super flexible and easy. And these workouts are going to appear in the calendar as I write them. And I can go back to the calendar view and see where they came from in the text. So this gives me a very simple way to visualize this note that I've been writing. The data entry is easy, but I still get structured views when I want them. All right, now I'm going to move on to the last system I'm presenting, which is called Riffle. Riffle is quite a bit different in focus than the previous two systems that I showed. Wildcard and Potluck are more targeted towards simple applications, less sophisticated users. And a lot of the related work in this area does focus on that demographic. Riffle started from the question of, let's see, is there some way we can bring these ideas from spreadsheets and databases to more advanced applications being built by more technically sophisticated users to simplify the creation of software? That's what Riffle is all about. So as framing here, one of the main problems that developers face when building traditional web applications today is that there are tons of layers in the architecture. So you might have a REST API talking between a rich front end and a backend server. You might have an ORM where you're manipulating objects in memory. You often have a relational database behind the scenes being queried in SQL. We're not done yet because even when the data is in the front end, we write JavaScript code to manipulate that data. And what you have here is essentially the same information being represented in many different ways, being queried with many different languages. There's a lot of manual coordination work typically involved in shuffling data back and forth across these network and process boundaries. And when you talk to developers, they often express frustration at just the sort of redundancy of this approach. Could we do simpler? So in Riffle, we build on this really beautiful idea called local first software. That name was coined by Martin Kleppman and collaborators in 2019. And the core idea is pretty simple. Get rid of this part and just keep this part. So what we're going to do is we're going to have the locus of sort of where the data lives and where the logic lives for our app with much more on the client. We'll put all the data on the client and treat the client as one of the sources of truth for this application. And we'll still have sort of synchronization between devices in the background if you're online. But in general, things are going to focus more on the client-side interaction. And what you get from this is a number of things. If you do it right, users will get faster apps by default because you're not always waiting on the network. Users also get offline mode for free because things are on the client. And the hope is that we can also give developers a much simpler mental model by getting rid of so many of these layers. Now, there's been a lot of projects in the local first space exploring different aspects of this problem. A lot of the energy has gone into figuring out the synchronization part, which is a really difficult problem. I'm actually not going to talk too much about that part of the problem, although I've done other work during my PhD that addressed that part. What I'm going to focus on more instead is this part of this diagram. Now that we've changed the architecture, how can we rethink the relationship between the database and the UI to simplify things? So here's the basic Riffle idea. We're going to choose a relational data model, and we're going to put a relational database in our client. And we can write all sorts of SQL queries directly against that client-side database in our UI. And the idea is to very tightly couple our UI to our database and drive the whole thing through these relational queries. Now, we also want reactive queries. So whenever anything happens to the database, all of our queries are going to automatically rerun. And again, in the background, this database is going to take care of syncing data to other devices and users for us. But the hope is that the application developer is mainly focused on this part. OK, now let's just see a demo to see exactly what I mean. So here's a pretty well-known benchmarking app called To Do MVC. It's just a to-do list app, essentially. And I'm going to show you how it's built using Riffle. So in this app, I can do things like write down to-dos. And what I'm going to do is open up a debug mode that shows you the contents of the Riffle database. So I have my to-dos table here. Every time I enter to-dos, you're seeing they're just appearing in this to-dos table. I can also sync that table in the background. So when I enter a to-do on one device, it shows up in another device, right? Now, interestingly, all of the state in this user interface, not just the to-dos, is stored in the database. So I had this other table called UI state, where actually, as I type into this form field, you can see it appearing there. As I set filters on the app, the filter field in the table is changing. Every single bit of state in this entire application is managed by our database. One of the neat things we get there is that it's persistent for free. So if I go reload that page, which I just did, this form field is saved. Your data is never lost once you've entered it. My debugger also shows you the live reactive queries that are running on the page. So here we can see the SQL query powering this app right now. Select star from to-dos. But a neat thing is that if I filter down to a different subset of to-dos, you're going to see that query change. So let's say I filter to active. That query just updated. And if I set to completed, we're adding a filter predicate to that SQL query that says where completed equals true or false. So what you're seeing is that Riffle is offering reactivity, not only relative to the contents of the database, but also the queries themselves can dynamically and reactively update as the state of our app changes. And with just those tools, you actually get enough power to represent essentially any interaction you want in this app. Next, I'll tell you a little bit about how this works behind the scenes. So our starting point for building this was this relational database called SQLite. It's very well known. It's designed to run in the client. We also started with a very popular web view templating framework called React.js. And so we take these two parts as given. And then what Riffle provides is a set of abstractions for binding those two parts together. So we allow developers to specify what we call a reactive relational graph. It's a graph of queries that have reactive dependencies on each other. You can write SQL queries. You can write arbitrary JavaScript computations as long as they're pure. We also support GraphQL, which I'll talk about later. And the basic idea is that we give you a set of abstractions where you can express this graph, say these are the queries I want over the data. Here's how those queries should be used by my UI. And then Riffle is going to take care of scheduling, reactively running all of these queries so that whenever anything happens to the database, your UI will be efficiently kept up to date. Now, one other note I'll make is that we've also built another version of this system more recently, which uses a different database that's not SQLite. It's a newer open source database called SKDB. And this database has a couple of key advantages. It has network sync built in, and it also has more efficient reactive primitives built into the database, which SQLite doesn't have, which help us with efficiency. So I'll be demoing sort of examples of both of these systems today. And again, the key point here is that once you've specified all these queries, you can kind of think of your entire app as just this graph of declarative queries. And any writes to the database coming from user interactions or anywhere else feed into this database through the queries, and you get an updated state of your app. Now let's look a tiny bit more at how you actually write this graph. Here's kind of the simplest Riffle component. This is a React component. If you've ever seen a React component before, this should look pretty familiar to you. And you can see here there's a SQL query, select star from to-dos. And we've assigned it to a name. And then we've used that name, to-dos, in our view code. So put simply, what happens is some write happens on your to-dos table. Riffle will notice that that table changed and automatically rerun this query. And then that will poke this component and say it's time to re-render this view. All that gets taken for you. Now, sometimes we also have more complex reactive graphs than this. We saw earlier we had a query that dynamically changed, right? So the way we did that was that we have our query from before, select star from to-dos, but sometimes we have a filter clause that goes in there. And that filter clause comes from the result of another query. This is a JavaScript computation which returns a string that's a little fragment of SQL. That JavaScript computation depends in turn on querying the database for the value of that filter that I set in the app, right? And so we have this data flow where I set a filter that updates this query, which updates this one, which then updates the query that's running here. We get new data. And then finally, in a sense, the view code is also a kind of query that depends on all those queries. So the last step is that we get the data we want rendered in this view. The whole thing is kind of this data flow graph that gives you a really clean mental model to think about. Okay, so I started off this segment about Riffle saying that we were targeting really rich, complicated applications. And so far, I've showed you a to-do list app, which is not the most complicated apps. And in fact, I haven't really proven to you yet that Riffle is beneficial for larger apps, right? Okay, actually, I'll do that in 1 second. I have one thing to show you first, though. So let's just look at this diagram again and talk about how Riffle works. In this case, we started from this underlying relational representation. And what we did is we have a UI component talking to that database with queries, and then interactions result in writes. All of my UI components are stateless and store all their state in this database. They can coordinate through that database. And once again, we saw our spreadsheet like table debugger appear to give us a sense of what's in that database. Okay, now let's get to a more complicated application. So to evaluate Riffle's ability to scale up, we've been spending the last year and a half using Riffle to build a music management application. It's called Overtone. It's developed by our collaborator, Johannes Schickling. He actually started out as kind of an external collaborator who was just building this application. And then he got so invested in Riffle that he actually became a collaborator in helping to build Riffle. And so the design of Riffle has been deeply informed by building this app. And his basic goal is a music app for power users that better serves the needs of people like DJs and hardcore music fans in ways that consumer music apps like Spotify and Apple Music don't support as well. He really wants things like fast performance and flexible data views. And he was having trouble finding a system that would be a good foundation to build that kind of app on. And Riffle sort of appealed to him. So that's how this collaboration started. I'll start off by just showing you Overtone. Here's the app. I've synced my Spotify collection into Overtone. You can see I can, click through my songs. I can sort these tables. I can click on different playlists that I have and navigate through them. I can play music. Let's see. Oh. Okay, there you go. You heard some music playing. I can, search my library. We have really fast search that lets you navigate your library. And it just has sort of the feel of a power user app over a large data set, right? Under the hood, it uses exactly the same primitives I showed you in the to-do demo. So we have, in this case, a lot more tables that contain all of your music metadata, as well as all the app state, the UI state. We have SQL queries. The relational queries are really useful in a music app because you can do things like express relational joins across things like tracks and artists and albums that are typically really annoying to express in a non-relational language like JavaScript. I mentioned earlier, we also brought in GraphQL. GraphQL is another sort of limited query language that provides this more concise syntax for essentially navigating graphs of associated objects. And we found that that helps sort of clean up some of our larger SQL queries as well. So now I'm going to talk about a few of the interesting user-facing benefits and developer-facing benefits that we've found from building Overtone using Riffle. The first one that we found is kind of interesting. It's the value of what we call synchronous transactional UI updates. So what that means is, let's first talk about the way things are normally done in a typical web app these days. The way things usually work is, here we have a little app. I click on something. After I've clicked, the app will go to a server over a network and ask for some new data. During that time, I'm kind of left waiting, right? We have to show something during that time. Maybe we'll show a loading screen, or maybe we'll just show the old thing that was there. And then at some point, maybe 50 milliseconds, maybe 1 second later, once the network traffic has happened and the servers responded, we get our new UI state. And we're very used to apps working this way. Here's Spotify, for example. You'll see as I click between playlists, there's sort of this black screen in between, right? That's sort of the loading state for the app. And it turns out this is annoying for two reasons. For users, you have to deal with these load times, which sort of slows you down as you're using an app. And for developers, it also forces you to reason a lot about asynchrony, because you need to think about this intermediate state that your app can get into while it's loading stuff. So in Riffle, we take a different approach, and we say, why don't we just load all the data at the beginning? So when you first load the app, let's slurp in all the metadata for all your tracks into this client-side database, so it's waiting there. Then once you click, we already have the data you need, so we can instantly respond to your query. And with no intermediate state, in a single tick, we can render the new UI state. So here in Overtone, for example, if I do the same thing that I did in Spotify, you'll notice as I click on these playlists, everything instantly updates together. There's not this in-between loading screen. And again, what we found is that this is good for users because they get a faster app. But perhaps even more importantly, developers get a simpler mental model because you can reason about your app as synchronously ticking forward between these consistent states. And you have many fewer intermediate states where you're dealing with different parts of your UI being in different sort of inconsistent states temporarily. Now, one thing I will mention, it's impossible to eliminate asynchrony 100%. Sometimes there's too much data, so we do need to go somewhere else to get it. For example, like we can't load all the songs that have ever been made onto your computer. And so in those cases, we do have to fall back to sort of a typical async loading workflow. But the idea is we can actually minimize that a lot by preloading as much data as possible. So I showed you earlier in the to-do list app that all of our UI state was saved by default. That happens in this app too. So I can navigate through this app, get into some state, right? I'll sort in a particular order. Maybe I'm in the middle of searching for something. And then I can reload and go away and come back tomorrow and get back to exactly that same state of the app. Now, importantly, the developer didn't need to build that as a feature or do anything special. It just comes for free because we're routing all UI state through this database all the time. There's some other, even deeper benefits here that we found really interesting. I can save snapshots of the entire state of my app at any point and rehydrate them later. I could even email you a snapshot of, a case where I ran into a bug, and you can load the app in exactly the state that I was in, pixel perfect. So we found that to be really useful in a lot of scenarios. Now, in terms of how that state was actually stored, Riffle has this neat sort of helper functionality where the developer can specify a state schema for a class of component. In this case, we have a track list component, which is rendering those playlists. And Riffle will help you automatically track state for each instance of that component that shows up in your app. So that search that I just entered there, it lived in a table like this where you can see that sort property, that search term. Riffle was tracking those for us. And whenever we go back and render that same track list instance, Riffle will automatically load that state. Another thing we found is that because we have this very clear declarative data flow structure for the underlying application, it's very easy to build debug views that help developers reason about what's going on in their apps. So here's an example. It's a log of all the updates that have happened in my app recently. And I can just see for each one, what was the write that happened? Which queries reran in response? And because we had that reactive graph that I showed you that's explicitly tracking all that stuff, it's very easy to provide these kinds of views that give you visibility into what's going on. We can even do things like download the entire state of the app and see it in a generic SQL database viewer. So here, I'm just going to open up a little debug pane and download the entire state of my app. I'll just open it up in the SQL viewer. And again, we get this really nice UI that someone else has built, giving us visibility into both the music metadata and UI state at that moment. Now, just closing this segment, I'll talk about a couple key limitations of Riffle. One limitation is that local first software is not a good fit for all kinds of apps, at least not yet. And there's a lot of active research being done on different parts of this problem. Obviously, data size is a limit. So if there's huge data sets that can't fit on your device, that's an issue. Access control can be more challenging without having sort of data hidden away on a centralized server. Because how are we going to control the access to data that you have on your device, right? Another issue is that when you have each device being its own source of truth and different people can be editing at the same time, even offline, you can get into situations where different devices disagree on what the sort of current state of things is. And if you're in a domain where you need stronger consistency guarantees, maybe like booking tickets for a concert or something, then this approach definitely has limitations in what it can support. Another limitation we found is that although the relational model is a very flexible way to model data, and we found that it works for lots of different kinds of apps, there are some kinds of data which are more annoying to represent. Sequences, tagged unions, these can be sort of awkward to represent in relational databases. We also find ourselves sort of taking data that used to be in memory state in a language like JavaScript and putting it in a relational database and taking it back out. And in those situations, we find that dealing with things like custom types and serializing and deserializing can sort of cause a barrier and sort of a bottleneck for developers that they have to work with. And so I think that's something that could be dealt with better tooling, but these are just some of the current limitations we've noticed. All right, so I showed you Wildcard, Potluck, and Riffle. Thanks for sticking with me so far. I'm going to close with a few brief conclusions, sort of zooming out from all these projects and thinking about what we've seen here, and then talk a little bit about some directions for future work that I find exciting. So there's this paper from the early 80s, maybe some of you have seen it, by Alan Kay that I really adore. It's called Opening the Hood of a Word Processor. And in it, Alan imagines, how could we make software feel more friendly when you pop open the hood like a car, right? And he notes that modern cars are really complicated. And so people are likely to be scared and unsure when they open the car hood. What they need is something more like a Model T. So this is a simplified model that's a little friendlier that they can have a better grasp of, right? And in fact, Alan actually had this really cool thought experiment where he imagined building a word processor using a spreadsheet in a Paint app. So when users open the hood of that word processor, they would see a spreadsheet underneath. Actually bears some interesting resemblances to the work I've shown. And I think one way you can think about what we've seen here today is providing friendlier views of what's going on inside of systems. So that when people, either end users or developers, open the hood of a system, what we want them to see is something that is ideally a simple enough view that they can gain some crisp understanding of the system. And hopefully it's a familiar view that they're already used to as well. And I've basically shown you two classes of tactics for achieving that. One is to take some existing structure that's a little more complicated and distill it and simplify it down into that simplified Model T view. So in Wildcard, for example, we take a web application which could have this sprawling, complicated implementation underneath. It has this very complicated, even the UI data structure could be really complicated. And we distill it down to this friendly table view that sort of reflects the essence of what's going on in this app in a way that sort of end users can deal with directly without having to worry about all those details. The other class of tactics I've shown is instead of papering over a complicated thing, just actually build the system in a simpler way to begin with, right? So in Riffle, what we saw is that the declarative structure of how we modeled the data flow in the application enabled these simpler views that help you reason about what's going on. We saw two kinds of declarative programming, actually. We saw reactive updates, which automatically handle propagation of dependencies. And we saw relational queries, which hide the details of query execution and just let you focus on the logical shape of the query that you want to run. And what we found in Riffle is that these two kinds of declarative programming really reinforce each other nicely. And when you have these running as the actual foundation for your app, what you get is the ability to implement all of these debug views that really help you understand what's going on. A really neat constant that's been true throughout the Riffle project is that the truth is we haven't actually put that much work into designing these views themselves. What's happened is that we've put all the work into modeling the app in the right way. And once you've modeled the app in the right way, building these views, it sort of just follows out naturally from the way that you've structured the application. Finally, I'm going to close with two directions for future work that I'm excited about. One is thinking about operating systems that offer data-centric interoperability. So if you've ever used an old school desktop operating system with a file system, you may remember back in the day when that was the thing, that we had the ability to coordinate between different apps through files. So for example, I could write a Word doc in Word and save it. You could open that same doc in Mac Pages and edit it, send it back to me. We weren't forced to use the same app. We could use files as this coordinating mechanism, right? Now in modern software, we've sort of gotten away from that. Apps like Google Docs or Apple Notes, these are applications which couple a specific way of viewing and editing data with the storage of that underlying data. I can't open a Google Doc in Apple Notes, right? And this has a lot of limitations in the way that we sort of use software. It means that if you send me a document, I can't use my preferred editor. I have to use yours. There's also limitations for people with disabilities. There's been great work done on how people with vision impairments struggle to use Google Docs. Before, they could just open a Word file in a different editor. Now they can't. And what I want to point out is that even though I've pitched Riffle to you so far as a tool for developers building normal apps, there's actually sort of a hidden motivation that I haven't talked about yet, which is that I think it lays a really interesting foundation for this kind of data-centric interoperability. What I mean is, so far I've shown you all these UI components being built by the same developer within one app. But what if we brought in other tools and applications from the outside as well to coordinate with an existing app through that shared reactive relational database? How might that feel? I'll show you a little prototype that sketches what that might feel like. Here we have an app. It's like a very early prototype of Overtone. And what I'm going to do is control its UI state through an external app. So I have this other SQL viewer connected to the reactive database. And I'm going to enter a search term here and hit save. And when I enter it, you'll see the search field here, update. Or, I've stored the sort order for the table on here as well, so I can reverse it. And when I hit save, you'll see the sort order update in the original app as well. So what you're seeing is I'm controlling everything that's going on in this existing app on my computer by connecting to the database that powers it using other tools. So I could build other kinds of custom views. I can script these apps through this database. I think this opens up a lot of possibilities. Okay, the next direction for future work, there's a very important word that I have not said yet in this presentation, and I have to say it because it's 2023. AI. Thanks, Daniel, for previewing that in the introduction. As Daniel mentioned earlier, I was very skeptical a few years ago about the role of AI in end-user programming. And things have changed a lot, needless to say, over the past year or so. We've seen that large language models are capable of doing quite sophisticated code generation tasks. And this raises the question, hold on, does any of what I just showed you matter at all, right? Can you just do this all in ChatGPT? And I think I say it kind of jokingly, but I think it really is an honest question to reflect on. Like, we're going to need to think hard about which parts of computing that have developed up till now are essentially going to be done in a fundamentally different way from now on. Now, I may be biased, but my personal opinion is that I don't think AI makes all of this obsolete. In fact, I think that LLMs go really well together with a lot of the things I've shown you today. In particular, I think these declarative abstractions for modeling applications and these live programming environments offer really neat opportunities for LLMs to slot in and help out with some of the parts that until now have been some of the most difficult for less sophisticated users to do on their own. Let's see an example of what that means. Let's go back to Potluck. So one of the things that I haven't told you is that we user tested Potluck with some people, and we basically found that programmers did great and non-programmers did not do very well. This was sort of unsurprising because our formula language was JavaScript, which is a pretty difficult language to learn. But it was sort of disappointing, right? It sort of makes you wonder how are non-programmers going to gain traction in environments like this? So in this demo, what I'm going to do is I'm just going to type in a natural language intent into that box. Let's say double the quantities. And I'm going to ask GPT-3 to synthesize a spreadsheet that does that task for me. And what it does, that's the automatically generated spreadsheet. In this case, it worked perfectly. And you can see it sort of achieved that task for me, but I still have a lot of visibility into what it did, right? So it generated these formulas for me. I see live data for what the computations are doing. I can even ask for an explanation of what it did. So let's see. I can click on that button, and GPT is going to auto-generate an explanation in English of what this spreadsheet does. It says, it extracts these things, it computes that value, then it adds a label in this column. And because it just generated code, I can jump in and look at and edit the code myself as well. So I can see, how does this doubling thing work? Okay. I can also change that number to 3 or 4 or whatever I want. That's a very fast direct manipulation interaction. And so what you're seeing here is sort of this hybrid approach where I still have all these affordances I had before. The AI is just sort of helping me make faster progress in this environment that's fundamentally centered around me having control of what's going on. And so that's my sort of optimistic view of this, is that these declarative abstractions, things like relational queries and spreadsheet formulas, are a really good fit for the current capabilities of code generation in LLMs, because they can help us generate these bits of code that we need to insert into these environments. And then the live programming piece makes sure that users can always inspect what's going on. They can see live data that shows you what's going on in the AI-generated results. And you can directly edit the generated code yourself to tweak things more directly. And this is an area of work that I'm really excited about exploring more deeply. I think over the coming years, sort of figuring out this interaction is going to be one of the key things to figure out in user programming. Okay, that's all I have for you today. Before I close, I want to give a huge thank you to my advisor, Daniel Jackson, my thesis readers, Rob Miller and David Karger. Every project I showed you today was done with collaborators. I've listed them all here, and I absolutely could not have done this work without them. So huge thank you to all the people I've directly collaborated with on these projects who are in this list, as well as institutions that have supported my work, the NSF, Relational AI, and Ink and Switch. And of course, to all my collaborators, mentors, family, and friends who have helped me along this journey. Thanks so much.
Thank you, Geoffrey. So we have time for some questions. I want to ask Geoffrey's thesis readers first, David and Rob, if they'd like to ask any questions at this point.
Yeah, I have two maybe little questions made that maybe I'll just ask both. The first is kind of about Potluck, which starts with the text as being primary and extracts a spreadsheet out of the text and then maybe puts some results back into the text. But there are plenty of cases where I might have actually started with the spreadsheets and then realized I wanted to have a nice visual view of it. So the calendar example is one. But I want to be able to edit the spreadsheet and make changes to the spreadsheet and see them reflected over here in the text, which seems to require not extraction patterns, but sort of template kind of stuff. Did you look at any of this? Do you have any ideas for how to have a two-way system where both sides sort of have equal status in
so to just, I'll briefly repeat the question. Did we look into making the spreadsheet directly editable in addition to the text note in Potluck? We absolutely did. It turns out to be a really tricky problem though. And the reason is that there are many possible text notes which can map to the same spreadsheet. And that doesn't really matter when you're going from text note to spreadsheet because they all sort of collapse to the same sheet. The problem is when you start making direct edits to the spreadsheet, you have to make guesses about which of the possible text notes you want to map back to. So concretely, like in my gym log note, exactly, our pattern language too general. So what happens is, imagine I wanted to log a workout directly in the table. I would need to figure out how would I represent that workout in the text in the best way. And I have to heuristically choose between many options. And we weren't able to find an approach to that we were super satisfied with, so we didn't include it in the system. But I think it'd be a really interesting thing to explore further. I do think it's very important that we found it to be very useful to have all of the state of the system stored in the text at the end of the day. So we didn't want to allow like an extra column in the spreadsheet that would be directly stored in the spreadsheet. We wanted to have the text always contain all the information in the system. So there's a number of reasons for that. Some of them are very pragmatic. It means that you can send this text document to someone and load it and everything's there. Textual affordances like copy paste.
So when you say everything's there, the text is there, but none of the formulas and extraction patterns. So in fact, what you really have is a more complete file. It does have code in it. And you can send that full complete file to someone.
Yes, that's totally true.
Full complete file could also have additional spreadsheet columns, right? So
that is totally fair. And in fact, you're totally right. When you share a Potluck document, you share a text file and a metadata file, which has computations. You can actually add a new column and sort of hard code. Like you could write a formula that just returns the number 5, and that would mean the state 5 is stored on every column or something like that. You could essentially represent state in that additional file as well. We felt, I guess the main thing is that we felt like we wanted the text to always be a full representation of the document. So for example, you should be able to close up that spreadsheet view and just work in the text note as the sort of sole representation and never have to worry about is there other state hidden away somewhere. That was one of our design goals. Yeah.
And the other question is in Riffle, where really pushing on this storing view state in the database so that you can see it on multiple places and so that it comes back when you reopen the application later. I want to ask where you drew the line on which view state we're going to store, because it seemed like even in your simple to view application, there was a cursor position in the search box, which was not a column in your view state, right? Why did you draw the line there? And what other places do you want to omit from view state most of the time? Like scroll positions. Where's the right place to draw the line?
Yeah, that's a fantastic question.
Repeat the question.
Oh yeah, repeat the question. So the question was, there are some pieces of view state which are not actually stored in Riffle. Things like the cursor position in a text field. Where did we draw the line and why? So you're right. We've actually done some experiments, interestingly, with pushing further than what I've shown today. We actually have done experiments with storing scroll position in the database and rehydrating from that. I don't remember off the top of my head, but I actually think Overtone might preserve scroll position as a stateful thing. But there's still stuff we don't preserve. We don't preserve like window size necessarily, or like mouse position. There's always going to be some state that was there. I would say in general, the reasons for where we draw the line tend to be pretty pragmatic in terms of the web browser itself and the DOM as a UI substrate have parts to them that are typically treated statefully. Things like scrolling, for example. To have really performance scrolling in a web app, typically what you do is you use the scrolling built into the browser. You typically don't implement your own scrolling view. And so given that typical way of using the browser as a UI substrate, I guess that would mean that you don't store scroll state as a default sort of starting point. And it takes active work to sort of opt in to storing those bits of state that are typically managed by the DOM. But yeah, I would say we go pretty far towards storing most state. And if you wanted to, you totally could store things like cursor position as well. There's no really like principled reason why you couldn't pull that off. Perhaps the one limitation maybe I should note is performance for some things is a bottleneck. So we've managed to get really performant round trips of UI state through our database, but it's very important that when you're interacting with UI, you want low latency interactions in a lot of situations. And so we are only really able to manage UI state in the database as long as round trips through that database can be fast enough to support UI interactions.
Great, so let me go to David and then open it up for general questions.
Absolutely, that's a great point. So the question was, when should you erase UI state? Because you don't always want it to be persisted from the user's perspective. It's a really great point. And the way I would frame that sort of is that today, the way we typically build applications is that we couple these decisions, like what UI state should persist and what UI state should be shared between users. We couple those to the fundamental architecture of the way we build the app. And what that means is that it can be very difficult to change these decisions later. For example, a lot of multiplayer apps recently, apps like Figma, if you're familiar with that, have started thinking about, maybe when I right click on a context menu, maybe my collaborators should actually see that context menu that I'm looking at, because then otherwise they just see a cursor moving around and they don't see what I'm looking at, right? But that's odd, because before you might have modeled that as ephemeral UI state, and all of a sudden now this is like whether a context menu is open is being synced through our data layer. And it can be very hard to change those decisions. In Riffle, what we promote is put it all in the database, have everything be savable and shareable, and you get to decide on a per bit of state basis how you want to treat it. If you don't want it to persist, just delete it when you reboot the app. If you don't want it to be shared between users, have it scoped by user sessions, and then don't look across sessions for the UI state. You could even imagine doing things like letting the same user have 2 sessions in different tabs or something very easily, right? The point is that these things become checkboxes. They're not architectural boundaries.
Geoffrey, actually, I want to just ask you a question about the same thing. You mentioned that scrolling would not be something you'd want to store, but I just want to check that I understand correctly, that there are certain aspects of the state which are handled entirely by the browser in a way that's invisible to the application. For example, if you mentioned the sizing of boxes, if those boxes were sized by responsive CSS and not programmatically, then presumably it'd be quite tedious to get them into the Riffle state. Likewise, scrolling of the entire page within the browser would be tedious, but the scrolling within a playlist, for example, where you're deciding which items to actually show in the playlist, is something that's already in the Riffle state. So there is still a question that there are some things that technologically are outside the abstractions that are easily accessible to Riffle. Is that correct?
Yeah, that's exactly right. The way I would put it is there are bits of UI state that take more and less work to synchronize with the Riffle database. So things like scrolling take active additional work from us to observe scroll positions, get them into the database, and then make sure that whatever scroll position is being shown in the app is actually driven by the database, because the browser also does its own thing.
David.
Again, separate the concerns. Like scroll position is like it's primitive quantity manipulated by the user. Right? Box sizing by reactive CSS. Look, that's a reactive value. It makes sense to store reactive values into the database because they're computed based on primitive values that should be. Right? Why would you store something it's going to be computed for other stuff there, right? But I think it's something that should be in so enough really deep on this one point. I want to ask you the same question about 2 of your different technologies. One is about this idea that really there should there should be a separate data modeling layer in your web applications that is accessible to the end user that you can pull out, make a spreadsheet view, add formulas, and the other is that, applications ought to be these database-backed things where the database itself is a separate layer and accessible to the program. So I think that we can look back at the past 30 years and see lots of research efforts that are driven by that concept, right? These things that they haven't tried the same way as we tried, but there are things that I think both of them are things that researchers, engineers say, of course, these are great ideas, right? This should happen. Everybody should be doing this. And then you look out in the real world, and it's not being done, right? Or it's being done much less than we expect, and many missed opportunities. And I wonder, do you think that's because we haven't quite figured out the right technical way to do it, or because there are sort of broader, out of context problems with using these approaches that cause them to be widely rejected, no matter how well we do them?
Yeah, great question. Just repeating the question, I guess summarizing, people have tried similar things before. Why haven't they worked is roughly the question. I think there are a couple different answers I would give to that. I think maybe one answer I would give is that a lot of the foundations of the local first approach we're taking in Riffle, there's a bit of a sort of, there have been some technical changes that have been happening in the foundations of the platforms we have over the past decade or so that have made the local first architecture more viable. So more powerful client hardware, computers and phones have lots of storage and lots of RAM, and that makes it easier to do the kinds of things I was showing you today. The advent of mobile made apps that work offline and in spotty network connections more important and more valuable. So those are some trends that we're looking into. I also think, maybe if I were to offer one hypothesis for why similar efforts may have failed in the past, I think that a lot of the really interesting research systems that explore different ways to build apps take the entire stack as part of the problem and propose an entirely new way of doing things top to bottom. There have been, for example, some really interesting projects that on this idea of, I think they're called multi-tier web architecture systems that basically manage the network boundary for you and let you write server and client programs together, things like that. And those tend to be very neat, but I also think they can be sort of difficult to adopt incrementally because they have such a full stack approach. A neat thing about Riffle, I think, is that even though you can imagine, taken to the very extreme, the ideas of Riffle do amount to kind of completely changing the way you build everything. The way that we've built it in practice is quite pragmatic. We reuse existing technologies for the view layer and the database layer, which builds on tons of work in both of those areas. And we just provide the language for binding them together, which is sort of the type of pragmatic decision-making that's enabled us to already build this quite sophisticated app using our research platform, right? And so I think maybe just being pragmatic about incremental adoption is part of the story.
Let me follow up with a question about one, I think, really pragmatic option, which is that this approach of separating out either approach. You pointed at how easy that makes it to use the application, to extract the data. So, if somebody's trying to make money off their application, it's like terrible thing. So that seems like a pretty severe obstacle to adoption, is taking out of the other wants to hang on.
Yeah, the question is, aren't these techniques bad for business because they make data more accessible, which essentially lowers the moat that your application has, right? I think there is hope. If you look at the way desktop apps used to work, there was some degree of lock-in from file formats, but actually over time, the trend of file formats has been towards openness. And in general, desktop apps compete on this is the best user interface and best experience we can offer you to edit this kind of data. And that's going to be our sort of competitive advantage. In the SaaS era, things have shifted more to these data moats where it's hard to switch because the data is locked up. I do think, though, that you can imagine business models, and this is a problem that gets talked about a lot in the general local first community, and other people have sort of tried experiments with real businesses built on a local first foundation, where they say, basically, look, you're going to pay us a monthly fee. The monthly fee is not because we're running servers. It's just to pay our development team. And you're paying a monthly fee because we're going to give you a great app. And part of the great app is that you'll be able to switch easily, and there'll be data openness for you. And that should appeal to you as a user, right? Whether that will actually work out in practice or be hopeless in terms of people leaving these services too easily, I'm not sure. But I wouldn't totally write it off. Maybe another answer is that's why it's research and not a startup.
Okay, so let's do this. Let's take some questions from those of you who are here in person, and then let's see if there's some questions from online. Yes, Arvin.
I love the work, Geoffrey. I was curious. I think I'm still trying to wrap my head around the Riffle value proposition. And I liked your slide where you had the back end, front end. I think at some point, and all the different layers that a developer has to go through. I think at some point you said, we don't need the back end anymore, right? And then you showed us the code of Riffle. And part of me was like, is everything old new again? Because that looked like the PHP code I used to write, where my SQL was embedded in the HTML that it would produce and things like that. But there's a reason that we ended up with the ORMs and all of these other things, right? It's often the case that the relational data model that I have imposes rigidity that doesn't map well to my user interface. And so I'm trying to figure out to what degree I believe your argument that we no longer need all those layers of abstraction, or is it the case that you imagine that those layers of abstraction just move to the client now, but that we will still need to recreate a data model for the UI that is distinct from the data model that is stored in the database, that we probably don't want to embed SQL strings all over the place, et cetera, et cetera?
Yeah, that's a fantastic question. Repeating the question briefly, Riffle code kind of looks like PHP, but that PHP had issues. Do we want new abstractions on the client side to replicate the abstractions that developed over PHP, or is the idea more to just have raw SQL and view components, essentially? So a couple things. First of all, it's a really great observation. And in fact, there's been this funny trend lately in web development more broadly of everyone realizing the same problem of, wait, what have we done? PHP was so nice. Let's go back there. And you have things like React server components, which is a new technology by the React.js team to essentially embed synchronous SQL calls in your React components that execute on a server. And people keep saying, oh, it looks like PHP. So the first thing I'll say is I think there was a real beauty to PHP, and it has a lot to do with some of the beauty of the Riffle model. In particular, in a traditional server-side rendered HTML application, you send some request to a server, it runs some code top to bottom to do some stuff, it spits out some HTML, and that HTML comes back to you. And during that response generation period, time is frozen. You actually don't have a live reactive system. You just have one snapshot view of the world, you compute something and send it back. And so you actually have, in a PHP app, a very, very slow synchronous transactional UI that round trips through a server. When we got to rich front ends, that's when a lot of these problems got really bad, because now we have state on the server and in the client, and we no longer have one loop. You might have a unidirectional data flow loop in React on the front end, but there's a bigger loop that you're missing. And so that's when things started getting more complicated. And so in some sense, one way to think about Riffle is like, it's PHP, but because it's on the client, you can pass everything through one loop. And so you can do more through that one loop. Now, I guess to really address the meat of your question, though, do we need more abstractions? I think the answer is yes. I think that there are a lot of places in our current state of Riffle where you can imagine better abstractions that would run on the client. GraphQL was sort of our stand-in for this abstraction for the moment, because we noticed, oh man, some of these SQL queries are getting very big and ugly and complicated, and a funny thing is every time we've talked to a front-end developer about Riffle, the moment they see a SQL query, they freak out and they say, I don't want to deal with that. Some of that might just be education and teaching, but it is true that SQL as a language has a lot of shortcomings. GraphQL was essentially developed to patch over some of those shortcomings, and so that's why we use it. But you can imagine other abstractions slotting in there. Examples would be like basic SQL query builders, or like an obvious thing that we've already started exploring. Variants on SQL or new relational query languages that are better suited to the needs of UI. The biggest problem is generating trees as results, which SQL can't do. So these are the kinds of things which I think could absolutely be amazing abstractions to add in and have running on the client side.
I think Henry next.
First of all, I want to say this terrific work. I think it's real. I think you managed to cut through a lot of the practical obstacles that have prevented, multiple instances to do this kind of thing or integration in the past. I was just going to give a quick rejoinder to Dave Carter about his comment about commercial thing. I think the situation that we're in now is, it seems like every week I get a new email system, right? The email of my bank, my health plan, and it's all I have in my regular email is something that says, oh, there's an update. So everything is, so this is nuts. We cannot, I think there's no, the problem with the walled garden thing is as time goes on, the walled gardens multiply. It's nuts. We cannot continue that. How many different file systems are there? How many different email systems are there? And I think this is just a phase, because this is not, this kind of multiplicity of interfaces is not sustainable. So I think the advocacies of commercial, competitive advantage have to tell us, the users, how we're going to benefit by all this crap. And I think, it's great to have projects like yours that shout from the rooftops, we have nothing to lose but our chains.
Yeah.
We've been chatting for a long time. I know we
can't stop.
The question is how to be impressive.
I might chime in with one extra thing. I skipped a slide for time that I'll go back to. One of the hardest things in the shared data layer problem is actually managing schema divergence. I've done other work during my PhD on this problem. The basic problem is, now you have multiple apps sharing data, but what if the apps want to share data in different shapes? How do they talk to each other? And then how can an app even update itself if it's sharing its data with the world? I think that's one of the other key challenges to address.
There was this updates, PowerPoints, and all that
Yeah.
stuff. But I recall the Jewish phrase, "You should have such problems." And that if those are our problems, we can deal with it. Problems we can't deal with are this multiplicity and inconsistency of interfaces.
Yeah. Yes, we have a couple of questions here. Yes. Sure.
Thanks, Geoffrey. Have you gone back to any of the educators in your introductory anecdote and showed them your work?
Great question. The question was, have I gone back to any of the educators from my anecdote and showed them this work? No, I don't think I have. It's a good idea, though.
You should.
Yeah.
I feel like that'd be so cool for them.
I will think about that. Thank you for the suggestion.
It's very
Yeah.
dignifying of their observations.
Yeah.
That was also one of our questions. Every time I've worked with educators kind of outside of our domain, they're like, what the fuck is that? So I feel like we don't actually understand how to use that and manipulate that. And I think your language model slide really touched on how intuitive interfaces, that kind of more technical thing can be developed. I'm curious, because you kind of briefly touched on this, as towards generalizing away from the relational model and as well to tree shape or kind of canvas shaped applications. Can you say a little bit about, is that thinking about why you should use the relational model? I love tables as much as the next guy, but in my experience, the reason that people love Excel is not because the title form is great, but the programming language and the domain model that you end users interact with the program is so much simpler than JavaScript. No, like straight backwards and all that kind of jazz. So I'm just curious as to how you're thinking about both kind of better, like different models, like if I want to go and manipulate a Figma tree or a hacker use comment tree and do something like a fold across that or polymorphism, like I don't know, like I'm just curious as to your thoughts about this. And then just one last comment, really cannot wait for the Riffle Emacs.
Yeah, okay. Thanks for the question. I guess I would summarize the question as what is this stuff limited to the relational model or could apply to other data models and applying similar ideas? So there are some pretty specific intentional reasons for picking the relational model. One of the best things about it is that it tends to be one of the data models that's most agnostic to the way that you want to query it. So a lot of tree models, for example, if you store your data as a tree, you're making a statement about how you intend to query it. That nesting sort of encodes some assumptions. And if you've ever used like a document structured database, a common problem that people run into is they model their data that way. And then later on, they realize they wanted to access it a different way, but the storage format has made that difficult. A big point of the relational model is to separate those two things and let you flexibly query the data the way you want to. And I think that benefit actually appears a lot in this. You see a lot of the benefits of that in this work as well, because different components can query the same shared state in the shape that makes sense for them. You can show different debug views of the same state. Some of them you could show tree-shaped debuggers if you wanted to, even with underlying relational state. So I think there's just a lot of flexibility that the model gives you that's lacking in a lot of other models. Also, it just naturally goes together with the table view. The table view is already familiar to people, and so there's a very natural kind of mechanical sympathy there between the spreadsheet-like table and the underlying relational model. But yeah, I mean, I think you could absolutely take parts of these ideas and extend them to other models too.
So I've got a little bit of a primordial point here. Applicator was really interesting because it talks about like modern cars being very complicated, like modern software is very complicated. And if you expect, anybody off the street to like open a word processor, it would be really scary. But a lot of the functionality that's there is sort of necessary to get the kind of functionality that people expect to have. Without it, it's not going to be great. Just like you're trying to drive Model T today, it's not really a good time. I do wonder about your thoughts. Is there a sort of complexity limit to which these sorts of approaches stop making sense? And I think Potluck is a great little example of this. It's like you express that there are a lot of these problems that you don't have for that a tool like Potluck can cover, but get beyond complexities of those sort of modifications, it gets a lot harder. So,
Yeah, great question. The question was basically, are there certain complex tools that can't be built in these systems? Where are the ceilings? So there absolutely are ceilings to the kinds of things you can build. At least Wildcard and Potluck in particular have very restricted sets of the kinds of tools that they're good at building. I can't make a word processor or like a video game in Potluck probably, right? That being said, I do think once you have an open-ended computational language like a spreadsheet formula language, you can go quite far if you bring in expert programmers to help you author those formulas. You can express quite sophisticated bits of computational behavior within a pure JavaScript expression, which puts the ceiling maybe higher than you might expect. And another really important point I'll make is that in a tool like Potluck, it doesn't have to be the case that everyone's always building everything up from scratch themselves. I think the workflow I envision is more something like you download an app from the App Store, it's a Potluck app, and then you can open the hood and change it a little bit if you need to, but you don't need to dig all the way deep into all of its formulas and things. So yeah, I guess, the basic answer is if we layer things so that you have the Model T view of the modern car, and you let people view and edit that Model T view, I think you can get a lot of mileage in simplifying the views that people see, and you can get pretty sophisticated stuff under the hood.
Great. Let's take two questions from the online audience and then close. Maybe Josh, you can read out 2 questions and Geoffrey can then answer both of them.
Sure, yeah. So the first question is from Benjamin Brody. He's interested to hear your thoughts on how your work might help people prototype faster, more cheaply, or improve the speed of design when writing applications.
Great. The question is, how do you make design loops faster? I think we've actually seen a lot of examples of that here. And the big technique is live reactivity. So seeing the data you're computing on, having it change essentially on every keystroke as you're molding a tool is very, very powerful for getting a fast feedback loop that makes it faster to prototype. In a lot of traditional coding environments, you might write some code, save a file, wait for something to compile, then reload some running thing, and there's a much slower loop. Whereas the tools I've showed today typically just have a much faster feedback loop through these live programming interactions.
Great. Great. Yeah. So the other question from Sala is, I think, about the last future work direction you were talking about with it. Combining LLMs with live programming and declarative abstractions. Seems like they were wondering about, does this bring up interesting problems with the ideas of once you get into sort of the database world about consistency or monotonicity or other things? I'm not totally sure. It seems like a sort of a stream of thought, like thinking, like what might be some considerations that you could imagine?
Sure, I can. So, okay, I'll interpret that as how do statistical methods like LLMs and symbolic methods like database queries go together? I think a really key point in this intersection is that having AIs generate code that does stuff for you and put it in an environment that you control is very, very different from having AI just do tasks for you. And so you're going to get a lot of benefits in terms of inspecting what it's doing. The speed and expense of executing things is going to be much, much cheaper if you can write code to do it. And so my rule of thumb right now is, like there are things you can do in Potluck that you could also do in ChatGPT. But in ChatGPT, every time I change the document, it's going to have to redo the whole thing, and it might mess up in ways that are unexpected. If I write Potluck searches, it can rerun them on every keystroke, and it still might mess up, but the ways in which it can mess up are more restricted, and I have more visibility, and I can be sure that certain classes of mess ups at least won't happen. And so I think thinking about when you want things to happen in this neural side of the house, and then when you want things to be more symbolically represented, and how you intertwine those two modes of interaction is basically the big question ahead at this intersection.
Great. Well, on that note, let's thank Geoffrey again.